Hey everyone, Thrasher back here. This is a short sequence of videos introducing something known as simple harmonic motion. We'll learn just what that means, a couple of vocabulary words that go along with it, and then dive into the first example or the first application of simple harmonic motion, which is pendulums, okay? So first, simple harmonic motion, it's a phrase that sounds frankly really complicated, but it's actually pretty simple if you think about how it is an object is moving, what it's describing. Okay? It's a term that's used to describe objects moving in simply an oscillating way. Think to yourself, back and forth, back and forth, back and forth. If there is an object that is doing that, it's a very good chance that it is exhibiting, it is showing simple harmonic motion. Now, what is causing this back and forth motion? Well, it's something we call a restoring force. To be honest, there are some more technical definitions for simple harmonic motion, but they all get to the same idea. It's an object that's moving in this oscillating, this back and forth motion due to a force of some kind. For example, we're going to get into some more strict definitions of pendulums later on. All right, but here I have a basic pendulum. If you don't know what a pendulum is, well, it's usually like a piece of string or something held at some point, and then you have a mass, and you pull it back some amount, and it swings back and forth, right? Well, just real quick, what is the restoring force? What is the force that is making this pendulum go one way and then the next, and then the other way and then the next, back and forth, back and forth? What force is that? It's the weight, it's the gravity force. If I pull something up here and then I let it go, well, gravity is acting on it. So it's going to start accelerating downwards. Now, it doesn't just stop right at the bottom because this little mass here would have some inertia. So it would still have velocity. It keeps going. Now it's kind of fighting weight, so to speak. The force of gravity or the force of weight is going to cause it to slow down and then stop and then repeat back and forth as many times as it keeps going before maybe friction, if there's friction, takes over. So that's all we mean. It's some back and forth motion, some oscillating motion due to some force. We'll see springs in a later video that is also due to a force. We'll get there, okay? Now, some basic words. There are some common words always used with this back and forth, this oscillating motion, this simple harmonic motion. The first word is period. Okay, the period of a pendulum, the period of a spring. Okay, period, and you've probably heard this term outside of a science context, and the definition is very similar. It's the time it takes. It is a measurement of time. That's why you see right here, it's seconds. That's the unit. That's how we'll measure period. But it's the specific amount of time for one cycle. Remember, we have this repetition going on, this back and forth motion. All right? Knowing the time could be helpful, but like what time should you use? Certainly as scientists, we all want to be on the same page knowing what time we're referring to. So by definition, we say that the time is the time for one cycle, and that's known as a period. What does that mean? So here I have a pendulum again. Okay, maybe I have some hanging mass. Here I have a wire, some string. It's attached to the top. Let's imagine I take this mass and I pull it back here. I'm holding on to it with my hand. Then I let it go. And the mass swings down. It hits the far end at the other side, and then back. That is the definition of one cycle for a pendulum. It's there and back again. I like this diagram because it has these arrows. So it goes there, this arrow, and then back. So T is the time it takes for that motion, there and back again. Okay, that's what we call a period. It's the amount of time for one of these cycles. But it's not here to here. It's not here to here. It's the time for one complete cycle, there and back again. Because after that, of course, you're just repeating that same pattern. So it might be helpful to think it's the time for one of those patterns. And then simple harmonic motion is just repeating that over and over again. All right, next term, frequency. Frequency, it's not a measure of time. It's you counting how many of those cycles, that's a number, 1, 2, how many of those cycles in a given amount of time. It's a number per time. Also think of a rate of cycles occurring. That's what it is. Now the symbol is F, F for frequency, okay? The units are a little weird. If I was looking at a pendulum, and I have a simulation of a pendulum right here, I'm going to pull it back, and I don't have a timer going, but let's say I was counting the cycles. There's 1, 2, 3, 4, 5. I counted those cycles. So I counted 5 cycles, And let's say I didn't have a stopwatch running or anything. Let's just say that took 10 seconds, okay? It didn't. I'm just making up a number. 5 cycles in 10 seconds. This is you measuring the frequency, how often there was a cycle, how often there was one of those patterns. You know, this could simplify to 1/2. This is what we would call hertz. The frequency of that kind of made-up example would be 1/2 hertz, okay? Now, this is the common unit, so Hz, that's what you put. It's also 1/s. This isn't as common, but you might see this written as 1/2 1/s's, or, you know, maybe 0.5 1/s's. Why 1 divided by s? Well, cycle, this was just me counting, right? It was just a number, 1, 2, 3. There's no numbers, or there's no unit, no measurement associated with that. So that's why it would just be something in the denominator, just the seconds. So that's why it's a little weird. This shows up every once in a while, but what's most common, just write down Hz, hertz, named after a scientist, okay? Now, there is something important for us to recognize about period and frequency. Now, in order to talk about this next part, sorry, I hit pause and I made my little drawing a little smaller so we could see it, but there's an important thing we need to recognize about this relationship between two words we just learned, period and frequency. They are, in fact, almost like opposites of one another. Remember, we saw in the last slide that period is the time for one cycle, and frequency, that's the number of cycles per time. They're opposites of one another, and that's actually an important relationship that can help you solve problems. They are inverses. The period is equal to 1 over the frequency. Or vice versa, the frequency of a pendulum or anything under simple harmonic motion, the frequency is 1 over the period. So if you know one of these two values, you actually automatically know the other value because they're flips, they're opposites of one another. They're reciprocals or they're inverses, okay? That's an important relationship that might not be on every equation sheet you are given studying physics, but important because if you know one, you therefore know the other, okay? All right, that's enough kind of broad talking about simple harmonic motion. Let's look at our first example. We've hinted at it, we've used it actually already. It's a pendulum. And first, something that's important when we're looking at these problems like for calculation examples, conceptual questions, especially on like the AP Physics 1 exam, we're talking about simple pendulums. That's an important distinction, okay? A simple pendulum is one where we're ignoring friction and air resistance, and that's pretty common, okay? We're also going to assume that the string has no mass. That's kind of funny, but we're just not going to take into account the mass, the inertia of the string. We're just going to say all the mass is at the bottom, right down here, okay? I'll get to this third bullet point in just a moment. Here's a diagram representing a simple pendulum. So, of course, it's something that's attached at the top. All right, we have some mass. Now, the mass at the end of a pendulum is often called a bob. So this is the bob of a pendulum. Kind of funny to say. Okay, remember, we kind of pull a pendulum back a little bit, then we let it go, and it oscillates back and forth and back and forth, okay? Now, when we pull back a pendulum, how far we pull it back is often called the amplitude, all right? How much you pull that pendulum back before letting go, that's known as the amplitude. Sometimes they might call that the displacement, okay? Sometimes they might even call that the angle. There's a few even different ways to measure it, but you might see a problem that says, okay, a pendulum is pulled back with an amplitude of theta equals 15 degrees. We don't do a lot of problems like that in AP Physics 1, but that would be this angle here between the vertical line and how far back you pulled the pendulum, okay? But just know it's pulled back some amount, and that amount it's pulled back is referred to as amplitude, okay? Now, this third bullet point that I haven't yet talked about, all right? For an equation we're about to see, and to really truly understand basic pendulum motion, what corresponds to a simple pendulum is this. We can't really apply certain concepts, certain equations. If I have a pendulum and I pull it way back, like if I pulled a pendulum back so it's 90 degrees, when I let it go, that's really turbulent, that's really chaotic, okay? Some simplifications break down. So a lot of times you'll see in problems, they might say, okay, we have a pendulum, we pull it back some small angle or some small amplitude, some small displacement. Don't worry, that word isn't really important. It just means we're dealing with a pendulum as a classic simplified object, okay? We're not dealing with really weird scenarios where maybe it falls and the string becomes loose. Just, it's a common word that College Board and other physics textbooks and professors might use. Don't worry about it, okay? It's just, it shows up a lot because it just means we can use the concepts and equations that we're about to see, actually, okay? So it's just a common phrase, but it doesn't change any of our thinking, all right? All right, I think this is my last slide. For a simple pendulum, not only do we have those certain assumptions, we kind of ignore the mass of the string and that stuff, but there's an equation. There's an equation for the period, the amount of time for one cycle of a simple pendulum. We're not going to derive this equation. Don't worry about, where it comes from. But the period for a pendulum, and I took this from the AP physics sheet itself, P here for pendulum, uppercase T here for period, all right? It is based on 2 pi, of course these are just 2 numbers, times the square root of L, where L is the length of that pendulum, all right? And we have G. G is the acceleration due to gravity. Acceleration due to gravity. Now, here on Earth, we know what to plug in. It's just going to be 9.8. This is not a vector. You don't have to worry about any negative signs. Just plug in regular old 9.8. Some problems, they might say like a pendulum on Jupiter or a pendulum on the moon. So it might change the acceleration due to gravity, but if it's on Earth, you're just plugging in 9.8 here. So how much time it takes a pendulum to swing back and forth? It's based on gravity, and it's also based on length. Okay, all right. To be honest, what might be a little surprising is it's not actually based on anything else. I have here a simulation from PhET. They have some great simulators here. All right, here I have a pendulum. It's swinging back and forth and back and forth. It takes some amount of time, right, for one period. Well, in fact, if I ramped up the mass over here and I made it instead of 1, I made it, 1.5. Well, I don't have a stopwatch. We're not going to spend too much time on this. We're not going to take any actual data, but the period didn't seem to change. In fact, if I make the mass way smaller, the period doesn't change. For a simple pendulum, the mass, it turns out, actually does not affect the period of the pendulum. Also, what doesn't change the period, which also might be a little surprising, is how much I displace it. This time from here and back is actually not any different than if I push it back even more. This time turns out to be the same. It's not in our equation. The amplitude, the displacement, isn't in here. For a simplified, simple pendulum, it's just based on L and the acceleration due to gravity. Okay? So that's kind of the basics of pendulums, the basics of simple harmonic motion, and there's an equation that goes along with a basic pendulum. All right, next set of videos, we're going to be looking at other things that undergo simple harmonic motion. That's it. I'm signing off. Thanks a lot for watching.